Hello, everyone. I'm going to go over this example by using the strong mathematical induction. So strong mathematical induction is kind of like in the regular form of mathematical induction. You assume that you first prove that it's true for the first number of your list, and you prove that if it's correct for PK, the statement PK is correct, then PK plus 1 is correct. It's kind of like this. In the regular induction, you prove that the first one is correct. Then you prove that if it's true for K, then it's going to be true for K plus 1. So in that case, it's kind of like you're saying that if it's true for 1, then it's true for 2. If it's true for 2, then it's true for 3. If it's true for 3, then it's true for 4, and so on. So that's kind of like the basic mathematical induction. In the strong one, you still prove that it's correct for the first couple terms, but you also prove that if it's true for all the terms less than K and including K, then it's going to be true for the next one. So it's kind of like this. You assume, like in the same form, you prove that it's true for 1, or the base is the first one, then you prove that it's true for all I less than or equal K, and then it's also true for K plus 1. So if you list it, it's kind of like this. If 1 is true, then 2 is true. If 1 and 2 is true, then 3 is true. Then if 1, 2, 3 is true, then it's true for 4. You know, like it goes in this manner. So actually you prove that this statement is correct. The right side is the strong mathematical induction. This side is just a regular mathematical induction. So I'm going to use that one for this problem. So how do we prove that? I mean, the first part, it says find the first 4 terms. First 2 terms are already given. S0 equals 0, and then S1 equals 4. Then if you look at S2, that's going to be, if you look at this one, it's 6 times. I mean, that should be, of course, this should be S, and that should be S. So you just simply add 6 times its predecessor minus the predecessor of that predecessor. So it's kind of like you're going to be, for S2, you need to do like 6 times S1 minus 5 times S0. So that's going to be 6 times S1, S4 minus 5 times S0 is 0. So that's going to be 24. So that's how you find S2. Now, if you want to find S3, S3 will be, so that's going to be 6 times S2 minus 5 times S1, which is 6 times 24 minus 5 times 4, which is S1. So it's going to be 144 minus 20, that's 124. Now we will prove this statement. Now, of course, I mean, it says the sequence given at the top is actually Sn equals 5 to the power n minus 1. So this is like your statement Pn, okay? So kind of what I will say is this is just true for every n greater than or equal 0. And as you see, it's true. Like if you look at S0, it's going to be 5 to the 0 minus 1, which is 0. That works. If you look at S1, it's going to be 5 to the 1 minus 1, which is 4. So that works. Now that those two are like your basis. We just prove that it's true for 0 and 1. Now let's go further. Now you will assume that this is strong mathematical induction. So we now assume that I mean, just we can say PK or PI. PI equals to 5 to the I minus 1 for all I less than or equal k, including k. And we want to prove that pk plus 1 is correct. Pk plus 1 equals to 5 to the power k plus 1 minus 1. Now we want to prove this. Now, this is, I'm sorry, this is not pk. We want to prove that sk plus 1. This is like si. That's a statement. So this is like si, the sequence, and this is sk plus 1. We want to prove this. This statement is pk plus 1. Predicate pk plus 1. So we want to prove this, and we assume that this is correct for all I less than or equal k, including k. Now, sk plus 1, by definition, remember what was the definition at the top? It was 6 times sk minus 1 and 5 times sk minus 2. Let me just write it down. So the original sequence was sk equals 6 times sk minus 1 minus 5 times sk minus 2. So according to this one, if I write k plus 1 here, that's going to be 6 times sk, it's just the predecessor, minus 5 times the predecessor of sk. So it's going to be sk minus 1. I hope this is clear. Just simply add 1 here to both. K plus 1, k minus 1. So this is the one by definition. It's given in here. So I want to prove that this is equal to 5 to the k plus 1 minus 1. I need to prove that. If I prove it, that's it. So by the inductive hypothesis, I know that for sk, this is going to be 5 to the k minus 1. For this induction hypothesis, we have inductive hypotheses. We have that, and then minus 5 times. See here, here's the strong mathematical inductions kind of like implementation. You, in the regular mathematical induction, you only look at the predecessor, but this time you're looking at more, like you're going more back, like you're looking at the predecessor of k. So you're going to k and k minus 1. You know, that makes it like strong mathematical induction. So so we're going to go with the predecessor of k, which is going to be k minus 1. So that's like, you see, that's going to be 5 to the power k minus 1 minus 1. So that's what we have. We plug those in. So now we want to prove that this is equal to 5 to the power k plus 1 minus 1. From here, I got 6 times 5 to the k minus 6. From here, I got minus 5 to the power, 5 times 5 to the k. This is like 5 to the 1. We're going to add the powers, same base, so it's going to be 5 to the k times 5 to the k. And then for minus, that will make a plus 5. So here, this part, I write this part. If you look at this part, oh, I'm sorry, I made a mistake here. This should be just 5 to the k, right? Let me just write it in the tail. 5 times 5 to the power k minus 1. So I distributed that one. This is like 5 to the 1. If I now combine this is going to be 6 times 5 to the k minus 6, and that's going to be minus 5 to the k plus 5. Now we can combine these two. These two will make -1, and that will make like 6 5 to the k's minus 1 times 5 to the k. It's going to be 5 times 5 to the k. So we got 5 times 5 to the k minus 1. It's kind of like you have 6 apples minus 1 apple, so it's going to be 5 apples. And here I have -6 plus 5, which is -1. So that's going to be 5 to the power k plus 1 minus 1. This is exactly what we want to prove. So that means, yes, it's right. This sequence sk, the sequence sk or sn is actually, therefore, you can say sn is actually 5 to the n minus 1. So that given sequence is correct. So I hope this example is clear. This shows, this is a great example, and a simple example for understanding the strong mathematical induction. There's a slight difference between the regular mathematical induction and the strong mathematical induction, but both of them can be used for proofs. For these type of problems, of course, strong mathematical induction is the best way. So I hope this example makes sense. Thanks for watching. Bye.